Okay, so now before we start to discuss about impurities and the impact of impurities, I think we should go back one step and discuss the phase behavior of CO2 in general, because that's always related to the impact impurities have. Many people talk about CO2 as a very special fluid, which is actually not true. So thermodynamically, CO2 is not a very special fluid. It behaves pretty much like other weakly polar fluids. It has just two features which are relevant for the whole CCS discussion and where this perception that it is something special comes from. The first point is that the critical temperature is relatively close to ambient temperature, so around 30 degrees C, and the critical pressure of CO2 is relatively high, close to the pressures which we find in pipelines. So usually when we have gas phase pipelines, we have a clear gas phase behavior of natural gas, whatever we transport. If we have water pipes, we have clearly the behavior of a hardly compressible fluid. With CO2 pipelines, we are always somewhere in between. We have a fluid that has density close to the density of water in typical liquid pipes, but we still have a relatively high compressibility. On the other hand, not as high as the compressibility of gases. So it's this broad range of relevant states which has an impact in particular on pipeline transport of CO2, on high density pipeline transport. And the other point that's important is that, and that's really unusual with CO2, CO2 has a very high triple point pressure, something like 5 bar. So at ambient pressure, only solid and gaseous CO2 is stable. We cannot have liquid CO2 at ambient pressure. And this means that if we have an expansion process, if we have an expansion process, this expansion can go into solid states. So the phase diagram we have to look at isn't just the fluid phase diagram, but we have to include the solid states here. So the pointer doesn't work well. This way it works. We have to talk about not only the vapor-liquid equilibrium, what we are used to from other fluids. We have to talk about three different phase equilibria. We have to talk about the vapor-liquid equilibrium, the blue area here, liquid vapor. We have to talk about vapor-solid equilibrium, and we have to talk about solid-liquid equilibrium. Solid-liquid equilibrium is something we will rarely face in CCS applications, but VLE and VSE are very relevant for CCS. And that's because if we look at typical pipelining states are at supercritical pressure, but slightly subcritical temperature. So if we look in this temperature entropy diagram, typical pipelining states are somewhere here. And this means that expansions from pipeline states can lead, if we expand to ambient pressure, they can and will lead into the solid vapor equilibrium area. No? It depends whether we look at the state in the nozzle, in the crack, or whether we look at the state after expansion. So there's the different, whether we have an almost isentropic or an almost isenthalpic expansion. But in any case, we will end up with states here somewhere in the solid vapor two-phase region. And This has consequences when we look, for example, at rupture scenarios. So this is a photo taken from the rupture of the Danbury pipe, and you see how much the surrounding has cooled down. So part of what we see here might be frozen water from the air, so condensed water that's frozen, maybe dry eye, it may be CO2 hydrates. So these solid states really become important in rupture scenarios, but also in expansion of pipelines during operation. The second point is, which also stresses how important these two-phase regions are, when we talk about tank transport. People talk about tank transport as transport of liquid CO2. That's not entirely true. We aren't in the liquid phase here somewhere, because when we have a tank transport, we always have a vapor head above the liquid CO2, which means that all states at tank transport are on the vapor pressure curve, or if we look into the TS diagram here, somewhere in the vapor-liquid two-phase region, close to the liquid, saturated liquid line, when we talk about a filled tank. But this means that temperature and pressure in tank transport are not independent. In tank transport, we are always somewhere here along the vapor pressure line. So also talking about a two-phase equilibrium. Now, this behavior of pure CO2 is well known. So we do have accurate property models for CO2. This is well understood, and also in high accuracy. We also have accurate models describing the solid phase of CO2, what we commonly consider as dry ice. This can be described in high accuracy and consistent to the models we have for the fluid phase. So that's property-wise not an issue. But now, if we talk about CO2 transport in CCS, and in particular when we talk about CO2 backbones, where different CO2 sources feed in, the situation becomes more complex. And that's exactly what we are talking about in COREu, about CO2 routes throughout Europe. We have CO2 from different base materials, from different sources, and we have CO2 captured with different capture technologies. So if we look at amine scrubbing, for example, typical uncertain impurity in the CO2 will be water, and we may see traces of amines and air components. If we look at oxyfuel projects, typical impurities are water, again, air components, and we may also see SOx and NOx in the CO2. If we look at pre-combustion capture processes, again, we will see water. Water is always an impurity we will find in the CO2. And we may see, for example, hydrogen or H2S, just as examples. Each of these processes by its own can be handled in pipelines. If we start mixing them, the situation is becoming more complex. And that is exactly the discussion we have at the moment. So from this, if we look at typical impurities, in the percent range, we will find impurities like nitrogen, oxygen, argon, methane, maybe hydrogen. So those components which are typically called the non-condensable gases, those are components we will find at relatively high concentration in the unprocessed CO2 after capture. In the per mil range, we will typically find water. And in the ppm range, we have impurities like SOx, NOx, H2S, amines. So we are talking about completely different percentage ranges or concentration ranges. And that's sometimes confused in our discussion. So when we discuss about CO2 purity, I frequently hear arguments like, we have 99.8% CO2 purity, we have almost pure CO2. But if you look at the typical concentration ranges, the amount of CO2, whether you have 95, 98, 99.8% CO2 in the mixture, this mostly is relevant for the concentration of non-condensable gases. Water and SOx, NOx, H2S are typically at much lower concentration. So even 99.8% CO2 purity leave 2000 ppm for impurities. So you can still have high concentrations of SOx, NOx, H2S, whatever. We are talking about two different levels. So the purity of CO2 is mostly relevant for the amount of non-condensable gases we have and not for the other impurities. So let's discuss the impact of non-condensable gases first. You know, if we have pure CO2, we are talking about a vapor pressure curve. So for a pure fluid, saturated liquid and saturated vapor in a pressure diagram, temperature diagram, form one curve, the vapor pressure curve. Now, if we start adding non-condensable gases, 1% of nitrogen, we see that the saturated vapor line hardly changes. That's almost the same as before, but the saturated liquid line, the pressure on the saturated liquid line, the line where the first gas bubble forms, increases drastically from just 1% of nitrogen. And what is formed in the pressure temperature range is this two-phase region here, where we have an equilibrium between a nitrogen-rich vapor phase, but not pure nitrogen. The vapor phase also contains a lot of CO2, and a liquid phase with little nitrogen. And the more nitrogen we include, the larger this two-phase region becomes. So the pressure on the saturated liquid line increases, and the two-phase region becomes larger. This has operational consequences, because in this two-phase region, for example, you cannot accurately measure mass flows, depending on which technology you use, but there are restrictions to that. It becomes very difficult to accurately measure the composition of the fluid, and it's not possible to use, for example, centrifugal pumps to further compress the liquid here in the two-phase region. So there are a number of operational constraints which essentially mean that you have to choose, if you want to operate a dense phase pipeline, you have to choose pressures which are well above this two-phase region to be sure that you do not get into the two-phase region unintendedly. That's the operational restriction. The more pressing point is running ductile fracture. Running ductile fracture is an effect that's due to the fact that the decompression wave, if you have a small fracture in a pipeline, the decompression wave is much slower in the two-phase region than in the single-phase region. And in the two-phase region, this decompression wave can be so slow that a crack grows faster than the decompression wave moves. And this means that along the tip of the crack, you always have the high pipeline pressure, even though CO2 is already escaping through a growing crack. And this gives a running crack along the pipeline, which needs to be stopped. So essentially, in pipeline design, you have to calculate the wall thickness against this criterion of running ductile fracture. And the arrest pressure for running ductile fracture, the fracture, depends on the pressure of the saturated liquid line. Huh? So on this pressure. So the higher the concentration of non-condensables is, the higher is the pressure you need to design pipelines for against running ductile fracture, which essentially means that the wall thickness of a pipeline increases, which makes the pipeline more expensive. And since the wall thickness in practical pipeline building is limited, because the pipeline needs to be welded on site, so the wall thickness is limited, it means that if you have larger content of non-condensable gases, the maximum diameter of the pipeline is reduced, and therefore the capacity of the pipeline. So an increasing concentration of non-condensable gases increase the cost for pipeline transport and limit the size of pipelines. That's a cost issue. We can deal in pipelines, we can deal with relatively high concentrations of non-condensable gases, up to maybe 5% or something like that. But then pipelining becomes more expensive as for highly accurate, highly pure CO2. For tank transport, the impact of non-condensable gases is that the filling pressure of the tank increases. So tanks, medium pressure tanks, do not have real liquefaction devices. They are filled to a certain pressure, and then over time, the pressure in the tank increases, and you have to deliver the CO2 before a critical limit is reached, which is typically at around 20 bar. So you will fill maybe at 14 bar, and then you have time until the pressure increases to 20 bar. And if you have more non-condensable gases in the fluid, the filling pressure, the initial filling pressure is higher. So you have less time for CO2 to be stored in the tank, up to a point where you cannot fill the tank at the typical temperature at all. No? So for tank transport, you want to have as few or as little non-condensable gases as possible to increase storage times and to be able to utilize the whole volume of the tank. So again, increasing amount of non-condensable gases increase the cost for tank transport. There's a third impact, and that's on storage sites. So when you have large amounts of relatively large amount of non-condensable gases in the CO2, the density of the mixture goes down, and therefore the storage capacity of each reservoir decreases. This depends very much on the reservoir. So if you have high pressure, deep reservoirs, the effect is visible. So if we have something like 5% nitrogen content, the capacity of the reservoir is reduced by maybe 10%, something in that order. That's a very rough calculation. Of course, in detail, depends on the structure of the reservoir. But there are cases where this reduction in reservoir capacity can be very drastic. And that's potentially for relatively shallow, low pressure reservoirs, where you see the large impact of the impurity in the extended critical region of CO2. So there is an impact of non-condensable gases on storage capacity. How big this impact is largely depends on the conditions in the reservoir. It has to be checked case by case. The second component we have at relatively high concentration, or the component which we have still at relatively high concentration, is water. And you have seen that water shows up in all our capture processes, and the phase equilibrium of water and CO2 is a very complex one, because water and CO2 are not miscible. We always get one one water-rich phase here on the left side with low CO2 content, and we get one CO2-rich phase on the right side of this diagram as soon as we have more than a certain amount of water. And the situation is complicated because at low pressure, we have a CO2 vapor phase. At high pressure, the CO2 phase is liquid too. So above this line here, we have a liquid-liquid equilibrium, not vapor-liquid equilibrium. The important point for us is in most cases in transport, we want to avoid a water-rich phase, because if a water-rich phase pops up, we will have high corrosion potentials. And for corrosion reasons, we don't want water to drop out, even not pure water. It becomes more complicated later on. But if we look at this diagram here, then the CO2-rich phase can solve about 0.2% of water. So from this phase equilibrium, we should assume that in a dense pipeline, we can allow for about 2,000 ppm of water, which is a lot. So that would mean that we have relatively low requirements on the amount of water in the CO2. However, there are other effects which are not described by this vapor-liquid equilibrium. And one of these effects is the formation of CO2 hydrates. CO2 hydrates are structures where a water molecule or a CO2 molecule is trapped in a water cage, and the result is an ice-like structure which can be formed at temperatures higher than the temperature where we would expect ice formation. So for pipelining, typical pipelining temperature, the formation of CO2 hydrates becomes relevant. This is something that's by now also relatively well described. So we do have models describing CO2 hydrates. Don't try to understand this diagram if you haven't seen it before. It shows the three-phase lines in the CO2 water system. And essentially, to the left of these outer lines here, you have to expect solid formation. And solid formation is something you don't want to see in any pipeline, in any valve. So you have to make sure that you stay to the right of these lines. And what's missing in this two-dimensional representation here is the third dimension, and that's the concentration of water in the CO2. It gets more complicated if there are other components which also form hydrates. You get an even more complex phase diagram, but all this can be calculated. There are models available for that by now, which can be used by everybody. So we know where we have to expect solid formation. Colleagues from industry are typically interested more in this kind of diagram, which essentially says that this is the water concentration in the CO2. And to the right of these lines, you have single phase, fluid phase. To the left of these lines, you can expect solid formation. And you see that, well, the temperatures at which you can expect solid formation are higher as long as the CO2 is in the gas phase. When the CO2 is in the liquid phase, the minimum or the temperature below which you have to expect solid formation drops, simply because the liquid phase can solve more, or the liquid CO2 can solve more water than the vapor CO2. Now, if you analyze this diagram, you find that, well, typical pipelining temperatures go down to maybe 270 Kelvin, maybe a little below in winter, typically above that. So about 250 ppm should be acceptable in the gas phase for a gas phase pipeline. If we look for pipelines with liquid CO2 or dense phase pipelines, then even something like 500 ppm should be acceptable. And if we look for tank transport, in tank transport, we are talking about much lower temperature. If we talk about medium pressure tank transport, we are somewhere here. So roughly 30 ppm of water should be acceptable for tank transport without a risk of hydrate formation. Now, if we look at the water content that's allowable in CO2 according to different specifications, on the right side you have the specification of Northern Lights, which says less than 30 ppm. Northern Light is medium pressure tank transport, so that's consistent to the value we just found for hydrate formation. If you look for Aramis, Aramis gives values for ship transport, also these 30 ppm, that's consistent. But then it gives for dense phase pipelines something like 70 ppm, and that's much lower than what we would expect from the hydrate formation side. Now, and there are other components, NOx and SOx, which are limited to very low levels, even down to single-digit ppm. And that's due to effects which have been widely discussed over the last few years, namely chemical reactions in impure CO2. It's these minor components which are really in the ppm range, like water, SO2, the NOx, H2S, whatever. I think those are the relevant components to start with. And essentially, all these components in the end lead to the formation of either sulfuric acid or nitric acid. And these acids have much lower dew points than water. So the limitations on pipeline water, but also on these NOx, SOx, H2S components result from the fact that if we mix them in a pipeline backbone, we get chemical reactions which in the end lead to sulfuric acid or nitric acid. And if we have a free acid phase from these components, we get corrosion rates which are simply unacceptable for pipeline operation. And that's why we are going to these extremely low concentrations for NOx and SOx. There is one commercial tool available which allows for calculations of these equilibria. Only MSC is something that's frequently mentioned and which is kind of a black box software. In principle, we know what kind of models is applied, but the parameters are not entirely published. And on the other hand, we have experimental results from IFE. They have published some results for 34 mixtures last year. And they distinguish between dropout of a corrosive phase, no dropout, and so on. So Oli gives for 19 out of these 35 mixtures at least qualitatively correct answers, which means, in my view, that we do not have any tool that accurately predicts these systems and answers whether we have acid formation or not. What's going on in particular in the CEN working group on pipeline transport is that based on such experiments, the industry tries to identify compositions which are safe for pipeline transport, also using means to reduce the oxidization potential in the mixture. And I hope that within the next year or so, we will find a composition which can be considered safe and is a reasonable compromise. But to me, it's clear that based on these experiments, we will never be able to find optimal compositions. Optimal in the sense that they minimize the cost of the transport chain. Because we have something like 6 components, at least 6 components which play a role. If you want to measure only 10 values for each component, this gives 1 million measurements, and we have published 35 until now. So we really, to find an optimum system, we need models which accurately describe this system. And that's something that's coming up where work is going on. In COREu, we do not address the work on these reacting systems. That's something that's partly addressed right now in the Norwegian project in Giga CCS, where we are involved, and hopefully soon in an upcoming independent EU proposal. We in COREu, we do not have the required power to address these systems. There's not just theoretical work required, there's also a lot of experimental work required. So that's something you cannot do within one PhD. What we are working on in COREu is another aspect. That's what Jana Schöne is doing in her PhD. So if you look at these lists of allowed components, you have a number of components which are specifically not allowed, or where just 0 is given because we don't have a reasonable value. And one concern I have with regard to these impurities is that 0 is just not a valid limit. So if we cannot detect a component in field measurements today, that doesn't mean that we cannot detect them somewhere in the lab. And it doesn't mean that we cannot detect the component with future measurement technology in the field. So whenever we specify that the allowable concentration of a component is 0, we have to expect that CO2 streams, which are on spec today, in a few years are off spec, simply because we have new measurement equipment. Among engineers, we may very easily agree that concentrations of a few ppb of whatever are not of practical relevance. But as soon as there are lawsuits about equipment which has failed or whatever, this is getting out of hand. And therefore, I think it's very important for us to find specifications for minor components, which are reasonably small to be on the safe side, but not 0. Well, because 0 specification as 0 can always become a problem. So what Jana is doing right now is she is working on a description of TEG and on the corresponding mixtures, and also looking for approaches how we can define concentrations for minor components with which we are on the safe side, that we do not get the formation of a second phase, but which are not 0. Yeah, that's it